Okay. Today, the least squares regression line, we actually did it last time, but like we're defining it. What is the least squares regression line? It's the sum of the squared residuals as small as possible. So those residuals that we were dealing with last time, if you add them all up and square them, that's how the calculations on the computer do the math. I didn't want to waste any of y'all's time and go through the math behind that or even explain it. I think you trust that computer applet to say, yep, this line is the least squares regression line. So what we'll do is we'll use it. The following table shows the foot length in centimeters and the height in centimeters for a random sample of 6 high school seniors. Use technology to calculate the equation of the least squares regression line. So would you please go to the applet and let's put that in. I will pause the video at this point for you to enter that data into 2 quantitative variables applet. That's how we'll do that. So you got your foot length in centimeters and your height in centimeters, and it's just a few points. So I clicked on begin analysis. Let me shrink this down a little bit, maybe not, and we'll slide her down. Get out of here. And there's a little button that says calculate the least squares regression line. We'll do it. It gives us this crazy residual plot, which we'll learn more about that next time. I thought we were going to do that today, but where did it go? Why do I not see it? You guys got it, right? What did you get? Yeah, I'll have to look back on why that didn't work for me. Sorry. But it's y equals what? It's that y hat, also that weird one. It's a weirdo decimal, right? 82 plus 3.307. 82 plus 3.3077x, is that right? Cool, thank you for that. And then that's just for these 6 high school seniors. So they say, you guys know who Shaq is, right? You guys know Shaquille O'Neal? He's still kind of famous, but he played basketball back in the 90s and early 2000s. Shaq's a big, tall boy, right? It says Shaq has a foot size of 38 centimeters. Let's use that information with this regression line to figure out what Shaq's height is. So since 38 centimeters is his foot, and that's our x, why don't you grab a calculator? You're probably going to need one of mine, like if we used them last time also. Yeah. 82 plus 3.3077 times, what was Shaq's foot? 38. This will give us Shaq's height in centimeters. According to this regression line, well, excuse me, we'll round it to the nearest centimeter also, because if you look in the table, they didn't have decimals. So would you call that more like 207 centimeters or 208 centimeters? 208. So I'll say about 208 centimeters. Well, that don't mean anything to me because we don't measure people's height in centimeters here in America, so I want to see how tall that is. So 208 centimeters is how many feet? Just out of curiosity. 6'8". What do you think? Definitely not accurate. Shaq is over 7 feet tall. Do you know why that's not accurate? Because you remember that cool E word where 38 was way out on the data list? Starts with an E. Extrapolation. That was an extrapolation. We used an equation for a bunch of data, and then this 38 was, it's not necessarily an outlier, but it's just way out further. It's extrapolated out, so the accuracy was not that great. So here is another bit of data about candy, how much sugar it is versus calories. They did all the math, or I did it for you. I punched it all in, made the scatter plot, did the regression line for you also. Which candy seems to be an outlier? Circle that dot on your piece of paper. There's a line. Which one of those seems to be the outlier? How do you feel about boom? That guy right there seems to be not in the data. Go find him in the charts. Which candy is that in the chart? Like the X value, Y value is pretty close to that. What do you think? Peanut M&Ms? Yeah. Seems to be an outlier. Peanut M&Ms has sugar of about 80 and calories of about 800. I was just kind of guesstimating, it's like 80, 800. It's yep, that's that guy right there. Then simple questions, just like the activity today. Where is this outlier in relation to that line? Above it or below it? That guy is above it. Cool. So here's what I'm going to do. So here I took out the outlier, and here that was the one with the outlier. Sorry about that. The one with the outlier. Didn't we just kind of say that it sucked the line up a little bit, right? And if you take out the outlier, things went down because they ask you what happened to the y-intercept. Well, this is the y-intercept of the original guy. This is the y-intercept of this guy. What happened to it? That's an equal sign, not a negative sign right there. What happened to it? Did it get bigger or did it get smaller? It got smaller because this outlier sucked that thing up, right? And wouldn't that make the y-intercept get higher in that case if that happened? And if you remove the outlier, the line was here. It went down a little bit. What happened to the slope of those lines? You know, like it is definitely smaller. Are you with me on that? But is it still almost the same-ish? You know, like kind of watch my teeter-totter. It's like if the slope would drastically change, it would go like whant, you know, or whant kind of thing with the teeter-totter. This slope, it is different. There's no doubt about it. But it's still basically the same kind of slope. So we'll say very lightly smaller or something like that, a little bit smaller. And you'll see how they word it on your homework program today, but for what I want to write down on these guys today, so like the y-intercept went down and the slope barely changed. The slope barely changed. And yeah, if you're watching this on a video, sorry, I'm doing a lot of stuff just physically in class. If you need help with that, come on in and see me and I will help you with that. That's kind of weird. Let's try another one of those right here. Here's a graph with measuring whatever they got, carbohydrates and varieties of beans and their protein. So cool. Would you be down with the fact that this dude right here is an outlier in all of that data, right? Totally an outlier. Let's see what happens if we remove the outlier. Record again. Holy cow. Look at where all the dots were if we got rid of the outlier. Would you believe that all the dots were kind of just all over there? And then this outlier is way out of the way. So this is the same graph of those dots. But it's just like if I got rid of the outlier, the regression line turned into that, like this guy right here. It totally turned into it. Because where is this outlier in relation to the line above it or below it? Above. If you think of this regression line like a teeter-totter, and this was a magnet, right? Wouldn't it just, boom, suck that thing up that way? It would like make it pivot because it's way far to the left on the graph, so it's going to suck it up. What did that do to the y-intercept? Increase. Well, I guess I'll do it the other way around. What if I got rid of the outlier? What would happen to the y-intercept? It was up here. Then what did it do? Go up or go down? Went down. Look at what happened to the slope also. The slope was a positive, was a negative number. Would you believe it came into positive number in that case also? Because it drastically, that magnet, wow, totally made that teeter-totter go down, person. And if I got rid of it, back to the dots, okay, it fits the dots more like that. So it's just like the outlier just gets sucked up like a magnet to this. So we're thinking as the regression line as a teeter-totter with a pivot point, and how would the outlier affect it? What if an outlier was way down here? Wouldn't it go, you know, just kind of like suck it down towards it in that situation? So the outlier is like a magnet for the teeter-totter. So I don't even want to necessarily write anything down on that. We'll just kind of keep going to the next dude. Here's another one. It says the scatter plot shows the relationship between this Jessel score and the age of the first word along with the least squares regression line. Two outliers. Boom. We've got a blue outlier, and then we've got, boom, green outlier. There were two outliers in that data. Let's talk about child 18. First, in English, in our own words, where is that outlier in relation to the line that the computer made for them? Above it or below it? Below. And would you also agree it's very far to the right on the graph? You know, it's like on the right side. So because the point for this child is below the line on the right, that's what they want us to put. The point is below on the line at the right. If I put a teeter-totter here, wouldn't that outlier suck it down that way in that case? What does it do to the y-intercept? It increases the y-intercept. What does it do to the slope? You know, it kind of just sucks it down, makes it negative. So let's see what this guy says. It's making the slope of the regression line more steeper. Like, the steeper it is, it's just like, kind of like this. It's just like, okay, this is really, really steep, and this is really, really flat kind of thing, you know, so it's making it steeper. So more negative is what the drop-down will ask for. It's like, because it was negative, it's going to make it more negative in that case. And increases the y-intercept. And to me, that's where the teeter-totter makes the most sense. It's like, what happened to the y-intercept? Well, it's kind of like this, and if it sucks it down, boom, doesn't that y-intercept have to go up on the graph in that situation? So it increases the y-intercept. How about child 19? That's up here. Where is this guy, above or below? Above, right? So it is, but it's also, would you agree, not very far to the left. It's not really that left, and it's not really that right. It's kind of in the middle of the data. Like, here's all the dots. It's kind of in the middle of the data. So if the line's right here, it's just going to do this. Wow. Sorry, there's a bump there. It's just going to suck it straight up. It's not going to really change the steepness of anything because it wasn't far left or it wasn't far right in that situation. So it says because this point is near the mean, that's like the middle, the average, and the homework program might call it this. If we remember back from a few weeks ago, remember that X bar? X bar is the mean, you know, so I'm going to just write that down. But above the rest of the points, it pulls the line up a little, which increases the y-intercept, but doesn't change the blank very much. What do you think should go in the blank? It increased the y-intercept, but it didn't change the blank, the slope. Yeah, if you just pull the whole line up, because the dot, the outlier, was towards the middle of the graph, it's just going to pull you up or down. It's not going to change your slope very much. Weird, you know? We'll try some practice problems. How do you feel about that? Like, all right-ish, you know? Because this next thing, I have an example before we even do the worksheet problem, this regression to the mean. I think it makes sense after 2 examples. So bear with me. If you're like, oh, that's kind of weird on the first one, Mr. P, you know, it's like, give me a couple examples to see if it makes sense. So this regression is what this whole lesson is all about. Here's a bunch of data. On the x-axis is how tall somebody's father is in inches. It's like, this is how tall your dad is. Cool. And then on the y-axis is if they had a son, they measured how tall their son was as well. So x-axis is height of the dad, y-axis is height of the son. And here's what they're saying. If those 2 dads and sons had the same height, any one of these dots would be on that line. Like, there's a dad that's got a height of 62 and a son that's got a height of 62. If they were exactly the same height, the dot would lie on the line y equals x, like that line right there. What do you think these dots mean if they're above the line? Who's the taller person? This is your dad height, and this is your son height. Is the dad taller than the son in this region, or is the son taller than the dad? Yeah. This dot right here, the dad is 60, son is 64. Isn't the son taller than the dad if the dots are above that line? Are we cool with that? Because that's the y values that we're looking at. The y value is the son, you know, the sons, the boys, you know, not the son. And then if we go below the line, who's the taller person? If we go below the line, that's where the dad was taller than the son. Kind of weird, right? Well, here's what happened. This is where most of the people fit, right in here. This is just kind of like your average stuff. And it looks like, if you just look at the dots, like half the dots are above and half the dots are below, you know, so it's just like, all right, there's really no evidence to say, like, who's going to be taller or anything like that. But they want to notice the weird thing. Over here, those are really tall dads. Like, their height, this is 72 inches, is like 6 feet tall. These are all dads that are taller than 6 feet, right? Those are really tall dads. And over here, what would these guys be? They're what kind of dads? They're short, right? Short fathers. So they kind of split it up into those. So look down here. Would you believe that everything down there is where the dad was tall, but how was their son in relation to that? Shorter or taller? Where are all the dots in red? Above the line y equals x or below the line y equals x? They are below that line. Every one of these dots is a tall dad, but the son is not as tall. He's shorter than the dad. You know why? Because the dad's tall, right? But these guys right here, there's just three dudes. Actually, they're the same height right there. These two are actually taller than their tall dad, right? They got a really tall dad, and the son is taller. So it's like if this dad is 6'6", and this son is 6'7". You know, it's like he's taller than the dad. Where are most of the dots at, though? Above or below the line? Below that line. Totally below. Here's short dads, right? Where are most of the dots at? Above the line or below? Above. Would you believe if the dad is short, it's pretty likely for the son to be taller than them, right? The son is taller than them because the dad is short. It's like, dude, your dad's short. Cool, I'm a little taller than him. Well, what that's called is regression to the mean. It's kind of like an opposite game. If the dad is tall, then the sons were probably going to regress to be short. And if the dads were short, the sons are going to be tall. That's called regression to the mean. And if you don't understand that right now, I totally get it. It's like, that was weird. I don't get that. Let's try the one on our piece of paper real quick. Do NBA teams regress to the mean? Well, of the 6 NBA teams that won fewer, oh, my bad. This scatter plot shows, like, how many games somebody won before the All-Star break in the NBA, right? So it's like, how many games did you win before the All-Star break? All-Star break's right in the middle of the season, okay? And then the other y-axis shows how many games they won after the All-Star break. What would happen if a dot was right there on the line? What does that mean? They won the same amount before versus after. Are we okay with that? So they ask us this. Of the 6 teams that won fewer than 40% of their games before the All-Star break. So let me get my cool little guy. These are all of the guys that won fewer than 40 games before the All-Star break, right? Because this is before the All-Star break, so I got to look to the left of 40. It says, what percentage did better after the All-Star break? I got to erase that dot that I put on there because it's not really there. So how many dots are above the line? Would you believe all of the dots? Every dot in this green region that I did is above that line. So what percent did better? This was how many, like, before the All-Star break, and this is after. Didn't these guys win more games after the All-Star break, right? What percent of them won more games after the All-Star break? 100%. Every single one of them, right? 100%. And that's weird. If you still are shaky on it, it's like, I don't get that, sir. Hold on, let's try another one. Let me delete that. Of the 8 teams that won more than 60% after the All-Star break. So would you see right there? They won more than 60 games, before the All-Star break. So they won a bunch of games early in the season. Where are the dots at in relation to the line, above or below? That's below the line. It says, what percent did worse after the All-Star break? It's also 100%. Right? 100%. Because they won big time early, and then, so 100%, sorry. Here's like the best school example I could think of before we even finish this. You know, like at the beginning of the semester, how everyone's grades don't exist, and then the first grade you get is usually a syllabus, right? And you get your syllabus turned in, and what's your grade after that? 100%, right? Don't you have like an A in the class after that? So that's cool. Then, would you believe, as the semester goes along, as we let time do its part, the grade that a person gets in that class usually regresses to what their average grade usually is. It's like, all right, it's just going to even out. So to fill this guy out and finish us up, explain your answer right here. Among the teams that did worse after the All-Star break, 100% of them had a better performance. Not sure what's that. Yeah. Right there. Yep. Better performance. After the All-Star break, likewise, 100% had a worse performance. The only thing I want to do before I let you start working on homework is just show you this. Like, Both of these cases, it was 100% of the time. What if there was one dot right here, and they said what percent of the people did worse? You would have to count up. I'm going to go over here instead. You have to count up that there's 1, 2, 3, 4, 5, 6, 7 total dots in that box, right? So you would have to say like 6 out of 7 and figure out what that is as a percentage point. You know what I mean? It's not always going to be 100%. You'd be like 6 out of 7 of them did that. Cool. All right, let's try some homework.